Hello, everyone. Good evening. My name is Sahand, and welcome to this presentation. Thank you for all the team preparing this event, and I'm glad to have a chance to participate in the Earth Day meeting and share our experiences and also get some information and knowledge from other groups and professionals about Earth and also our nature. So before going my presentation, I'm going to start to briefly introduce our association, student association at USF, American Waterwork Association, student chapter at USF. I'm the president for this organization, and we are a group of graduate students with me, Adeline Beric, and Isabella Silverman in our group, and we have our organization to join different meetings regarding water, wastewater, environmental engineering, and also sustainable development projects. So during the COVID, we tried to make different webinars and also joint programs with Ontario Water Environment Association about water and wastewater treatment technologies. And we had a lot of students, professionals join us. So hopefully in the future, we'll have some other events, and you can find our association through the LinkedIn and also our email. So as a research in University of South Florida and part of my PhD research, I'm going to talk about role of algae in nitrogen removal and energy recovery from wastewater treatment. So this research is under supervision of Dr. Serena Ergas and Dr. Kung Zhang at Department of Civil and Environmental Engineering at USF. And as an introduction, I'm going to talk about wastewater. So in a simple definition, wastewater is the effluent from household or industry, which has contaminations or hazardous chemicals over the standard level. So we define it as wastewater. Generally, wastewater treatment consumes energy and also chemical. In case of the energy, it's been reported from the articles and also literature that around 1 to 5% of total national energy consumption in Europe is going for wastewater treatment. And in the USA, it's about 3 to 4% of total national energy consumption. So regarding the energy consumption, it's not negligible number, and generally we say 0.3 to 2.1 kilowatt hour per cubic meter of treated wastewater goes for the energy for the treatment. So let's talk about energy recovery from wastewater. The most common energy recovery system is anaerobic digester, as we heard information from Nilofar's presentation. So this technology is not new, and people from old years, they use this technology because it's reliable. And in a simple configuration, we have aerobic system in treatment plant, anoxic system in treatment plant, and then clarifier. The sludge we get from clarifier is going to be used inside the anaerobic digester. And inside the anaerobic digester, after production of the biogas, the side stream effluent consists of high concentration of nitrogen and phosphor. So generally for nitrogen, we define it as high ammonium strength wastewater. So its concentration for the ammonium is around 400 to 2000 milligram per liter. It's very huge number, and conventional treatment systems cannot afford this wastewater, and we need some specific technologies. Generally, we have 3 scenarios for this side stream effluent. The first one is direct recirculation of side stream to the main stream, and then okay, we say let's reconnect to the effluent and then use it again in the mainstream system. But it's important to know that this way can inhibit all the biological nitrogen removal process in the plant, and it can inhibit the reactions like nitrification and denitrification, because it can poison all the organisms inside the treatment plant according to the concentration, high concentration that we have. Or it can change complete configuration of treatment plant and then make problem for the other reactions. The second scenario is releasing side stream into the environment and nature. We can say that, okay, I'll leave it to the environment, and then we can use rivers for this and forget about side stream. But the problem for this way is soil and water contaminations, and then that can provide eutrophication, which is trending currently in the US, according to river contaminations and also a harmful algal blooms. In any place we see like green water, it means that we have eutrophication, and then there are some contaminations that can kill fish and other organisms, living organisms in the water. The third scenario, which is the engineered one, is side stream treatment before recirculation. It means that we can provide a treatment system to decrease the nitrogen loading rate of this high ammonium strength wastewater, and then provide like normal concentration to the mainstream as influent. So this technology needs, again, some specific configurations, and like conventional treatment methods cannot prepare required technologies for this, and we need to find out first the reason and then suggest the solutions. If we consider biological nitrogen removal process, as you can see from the chemistry we have, I'm not gonna go further about this chemistry and then talk about some details, but it's obvious that we have oxygen consumption in our reaction, and also we have organic carbon consumption and carbon dioxide production. So these three keys are very important. We need to control oxygen consumption in order to control the aeration. We need to control organic carbon consumption in order to control carbon dioxide production, and then greenhouse gas generation. That's not negligible in wastewater treatment plants. So if we talk about the aeration and also oxygen consumption, we have around 50 to 75% of total energy in plants going for aeration. And if we talk about kilowatt hour, it's about 0.18 to 0.8 kilowatt hour of the energy per cubic meter of treated wastewater. So that's the energy consumption according to wastewater treatment. For a simple configuration of biological nitrogen removal, we can describe it in four-step reactions: oxidation and also reduction, through the nitrification process and denitrification process. And according to activities of ammonium oxidizing bacteria, nitrite oxidizing bacteria, and heterotrophs. So for the first section, we have oxidation of the ammonium to nitrite, and then oxidation of nitrite to nitrate, or NO3. Then it's going back to reduction, NO3 to NO2, and then NO2 to nitrogen gas. This is a cycle of nitrogen removal in a wastewater treatment plant, but we have 75% of oxygen in the first reaction, 25% of oxygen in the second one, and also organic carbon in the first reaction of reduction as 40%, and then 60% in the second part. So what can we suggest as an alternative technology? The alternative technology right now is shortcut nitrogen removal. Through this shortcut nitrogen removal, we can cut two reactions and then only have oxidation of ammonium to nitrite, and then directly nitrite reduction to nitrogen gas. So in that case, we can save 25% of the oxygen in our treatment and 40% of organic carbon in the system. So we provided another method at USF in order to save more energy for the aeration, and that's using algae for shortcut nitrogen removal. We provided the technology to implement this shortcut nitrogen removal system inside algal bacterial environment and providing light and dark conditions to make aerobic condition and also anoxic zone for heterotroph bacteria. So I should mention here that the reason we use algae is that algae, like plants, can provide oxygen under light conditions. So we can use this potential to provide and pump oxygen naturally inside the system by giving the light condition. And then we don't need to use any external aeration in our system. We can save 100% of oxygen energy or aeration energy. So the aim of this research is taking a bench scale or lab scale system, use the regional conditions around the US according to light intensities and also different temperatures and also different conditions in each states, and provide design parameters for large scale and implement in full scale systems. So the tools we have are experiments to find out the operating conditions, find out the best operating condition for our target concentration at the effluent, and also use mathematical simulation and modeling to provide the information and predict our system before construction, and predict that, okay, if we run, for example, this system at Florida, what's going to be happen the system in, for example, Seattle, as you can see in the map, according to different light intensities or different climate there. Or what about cold area and also warm area? So we can provide those information through the modeling and simulation for this system. So in order to develop a model for this, we got the information from light intensity during the summer and during the winter from Tampa International Airport, and that's light intensity. So people measure light intensities in the airport and then reported during the years and decades that, okay, for example, for during the summer, what is the maximum light intensity? And during the winter, what is the maximum light intensity? So we found that during the summer, we have around 1400 micromole photon per meter square per second as photon flux for light intensity that we define. And also during the winter, we found that it's half of that value, around 700 micromole photon. So that gave an idea to make a comprehensive model for, let's say, June and January, and find out the mean design parameters for our system, and then implement these light intensities in the lab according to the equations that we use as Beer-Lambert law to provide light intensity and convert it from actual light intensity to the lab scale light intensity, because in the lab scale, we cannot provide this huge number, and that can degrade and then kill all the algae we have in our reactors. So we scaled down the actual system, made a model for June and January, and then we try to scale up through the model we developed. The results from our model and simulation showed that in a 24 hours cycle, we have oxygen production as 3 milligram per liter in our system by growing the algae. And we have ammonium removal, like around more than 90% ammonium removal by producing the oxygen, and then give it that oxygen to ammonium oxidizing bacteria. When we have algae growth and oxygen production, we have bacteria activity because they use the oxygen produced by the algae and then grow, and then they try to oxidize ammonium. And during during the light condition, we try to minimize our ammonium available in the system to the 0 milligram per liter. And then as we remove our ammonium, because it's going to oxidize to nitrite, we have nitrite production, and then it's going to reduce to nitrogen gas during the dark condition. Then we don't have any more nitrite also in our effluent. Since we use shortcut nitrogen removal system, the aim of shortcut nitrogen removal is suppression of nitrite oxidizing bacteria or inhibit nitrate production. So our models show that, yes, we are in the standard range of operation, and we are at the exact shortcut nitrogen removal system, since we don't have any NO3 or nitrate production in our system. And that shows our model well fitness and also our experiments validity. So as a conclusion, we found that using this system doesn't need any external aeration. We can remove more than 90% of nitrogen in our wastewater, and then we can produce 300 milligram per liter per day algae. This algae is valuable for us because we can convert it to biofertilizers, biodiesels, or animal foods. So the idea I used for USF innovation startup was implementing this system and production of biofertilizers and sustainable resource recovery from wastewater. So the design parameters and optimization for algal bacterial shortcut nitrogen removal requires target concentration. We have different, let's say, different customers and different targets for their nitrogen. For most cases, we cannot remove 100% of nitrogen because our customer may ask that, okay, I need, let's say, 60% or 70% of my nitrogen removal, and then I can use the leftover nitrogen remain in the system to another inside the another process of the treatment plant. So our model can predict in that case, okay, for this target effluent, what's going to be the system, appropriate system, and also design parameters. Also, according to the states and also regional conditions, we can provide through the model different operating conditions and then find out the optimized value for operation. Also, we can define different design configurations that we need to use any raceway system, any plate reactors, any tubular system, or any cylinders for algae production. So through the model, we can predict this, and also algae harvesting capacity. Again, according to regional conditions and light intensities, we can provide information for algae production and also value for our operation. Finally, we can provide cost analysis for our photobioreactors according to design parameters. We can estimate and also optimize from our model. Right now, we are working on case study in Pinellas County at Florida, and they are using anaerobic digesters in their plant, and we try to get a portion of their side stream effluent and then implement our idea and see the results, and then validate to another case studies and also real plants. So this was a brief introduction for our research regarding algae and also energy and resource recovery from wastewater. Thank you so much for your attention. And if you have any question, I would be happy to answer. And you can find me through the LinkedIn and also email provided here. Thanks.